So do you have an application that has some requirements around scalability and continuity of service? Well, what happens if your service gets hit by some heavy load? Does it have performance problems or reliability issues? Or even worse, cause some kind of impact to your solution? Well, this is where several patterns could really help here that Will Eastbury and myself will be talking about today in another episode of Cloud with Chris. Hello and welcome back to another episode of Cloud with Chris. You're with me, Chris Reddington, and we will be talking about all things cloud. Now, once again, this is another episode in the series of architecting in the cloud one pattern at a time. And I say one pattern at a time, but we're going to be talking about a few in this session. And I won't introduce them. I think it's only fair that I bring in, once again, the man of the hour, and delighted to have back with me, Will Eastbury. Hello, Will.
Hello there. Thank you for having me back.
No, very welcome. Glad to have you with us. And I think based off of last session, we thought one pattern's not enough. We've got to go ahead and do three at once and see how we handle those ones. So we can have some fun in this one, I think.
Yeah, absolutely. I think it's only fair that given that these patterns are connected and used together very, very frequently, that we should bundle them up, I think.
Absolutely. So I guess then we should jump across to the screen here, and I think there's going to be three patterns we're talking about. So queue-based load leveling, competing consumers, and the asynchronous request reply pattern. There's a reason I didn't say those in the intro, because my tongue twisters are not good first thing right here. But I guess we'll start, I think, with you tell us. Does queue-based load leveling make sense to start with?
I think so.
Sure.
If we describe the kind of sample scenario that we were thinking about and how these are generally used in practice, I think from therein they kind of logically fall into a sensible order. So the first piece is around talking about a theoretical kind of high load, high throughput scenario with dramatic peaks and troughs in demand. And the example that we always use around that is a ticketing site for a major event, where scale will go from nothing, from no requests at all for 24 hours, to a sudden burst of 100,000 to 200,000, or if it's something like the FIFA World Cup, to 10 million ticket issues in 4 minutes, and then back to nothing again. Normally, what happens with these sites is they crash. Generally, because people don't necessarily implement these all the time. If you see a site that's capable of handling that kind of peak and trough in demand, they will have implemented all three of these patterns. It's almost certain, whether it's in Azure or somewhere else, but they'll certainly have implemented some variant of these design patterns. So if we go after the first piece, Chris, which is around how do we handle a sudden spike in inbound requests? Yeah, and this is, I think the description of this queue-based load leveling is, it's a very long stack of words for a concept that's pretty simple, to be honest. And a nice example of that is the drive-through. Yep. So if you suddenly get 3,000 cars arriving at a restaurant, you don't try and fit them all into the car park at once. You tend to find them forming an orderly queue along the road outside, and then they gradually make their way through one by one, and they get served in order when the server has time to actually handle each request. Yep. And then we move on to the next one, and then we move on to the next one, and then we move on to the next one. But at no point do you actually, unless somebody decides they don't want to go into the car park or into the queue, at no point do you actually lose any requests. Yep. So we simply create a buffer or a queue of requests, pop each request that's coming in. So each ask for an inbound ticket. Yep, your user goes on. So Chris heads on and he wants his concert ticket, jumps on, and he literally takes his place in the queue with another 340,000 people. Yep, so his request, it might be number one, it might be number 349,999. But the guarantee that generally gets offered by any queuing platform in this context is they're processed in order.
Yep.
Yeah. So the first person who got into the queue is the first person to get the ticket. and then the second, and then the third, and those are processed generally in a first in, first out manner.
Gotcha.
Now, there are different kinds of queues that we can have, but the one which you use in this context is first in, first out. And the benefit that gives us, we can scale out lazily.
Mm-hmm.
So you can take the amount of, in fact, there's a nice image of this further down. So we go to this one. Yeah, we've got a number of things, which are our tasks on the left-hand side, popping messages onto a message queue at a variable rate. So we don't know what the demand process is going to be. We might have 10 people on the site. We might have 1,000 people on the site. We might have 10,000 people on the site. All we need to know is that regardless of what that variable rate is, the service which is doing the queuing is able to sustain that ingress rate.
Yep.
Yep. And hold those messages until we're ready on the back end service to process the next one.
And there's an interesting point in that, and I'm going to bring it back to the analogy. I've got to make a nice real world observation / joke. There's a fast food restaurant near me, I'll leave it unnamed, that's, let's say, going back to your example about the cars lining up, queuing up through a car park or whatever. Every single time that car park completely backs up, and anytime the queue gets long, it goes back onto the roundabout, it starts impacting all kind of local areas. And I think there's a point, stick with me here, there's a point in there about things like the queue size as well, and just making sure that any technologies that you use for this kind of pattern, just understanding, what is the maximum message size, what is the maximum size that the queue can handle, and things like that. Because if you don't plan for those scenarios, just, I'm being loose in my example here, but it could have some downstream impact and wider impact then as well.
No, that's absolutely right. I mean, that's actually a key consideration. So the depth of the queue, the number of messages that can be sustained inside it, and the volume will vary between queuing technologies and implementations. Yep. So it's important, and in fact, in a lot of them, in particular, like Azure Service Bus is one where you can choose the maximum depth of the queue. Yeah, so you say, I want a queue that is this big because actually my downstream service can only take this much. Yep. Yeah, so it might vary out and maybe level the load as it comes in and smooth out the peaks and troughs in demand to a constant rate that your service can process. Yeah. But there might be a point where after I've taken 20 gigabytes worth of requests, there will definitely not be any tickets left anymore. Mm-hmm. So I never want the queue depth to be bigger than that. Yep. Because it's pointless. So that kind of scenario, and that would be the situation where your restaurant eventually runs out of food because the queue got so long.
Yep, exactly.
Yeah,
exactly.
Yeah, so that's absolutely a valid real world point as well. And let's stick to that. Let's give the real world analogy and the and the technology type analogy as well. Yeah. Cool. So if you've ever seen what happens with a lot of customers and organizations at Black Friday, where they use a virtual queuing system to throttle the number of people coming onto their site. Yes. That's something subtly different. Yeah. So what they do there is they throttle the opening page. And I've never been entirely sure why organizations tend to do this. I think it's because they might have a legacy type architecture or a kind of monolithic architecture that you can't implement this queue-based load leveling pattern behind the scenes. So what they're trying to do is to control demand, rather than queue requests. Yes. So they're trying to throttle it at the point before that, right? And that's kind of the real world analogy to that. It's almost more like having a nightclub with a doorman, that can only contain a number of people inside the club at any one time, and it's a one in, one out policy. Yeah, and I think that's a really good analogy. Again, I love analogies, and I think it's to do with that underlying capability, right? If you think it is, the retail example, potentially a legacy application, it's using some heavy compute under the covers to dynamically generate pages, to pull things from the database. If you have that influx of customers coming on, you are instantly going to crash that application. That's without a doubt. As opposed to something a bit more cloud native, where maybe it's a static website and behind the scenes it's using those queue-based load leveling patterns and whatnot. Yep. That would be the difference, wouldn't it? And I think that's where we say that monolith piece is probably going to be the challenge there, or more likely be the challenge there. Yeah. Yeah, that's fair. I mean, there's a lot of e-commerce systems that have a hybrid approach as well.
That's true.
So if you're using an off-the-shelf storefront package, then obviously you don't have control of what's happening inside this environment. So what they'll often see is that kind of inbound gateway throttling produced by some kind of advanced CDN, where they're queuing people coming into the store so their storefront can maintain demand and actually stay up. But then the fulfillment platform behind it will be running in a much more natively queued ordering type fashion, so they can sustain the back end. So yeah, there's ebb and flow, and there are changes as to what people can or can't do within the platform. But definitely this pattern, so queue-based load leveling, is around trying to maintain a consistent level of performance in the face of widely varying demand.
Gotcha.
So it's key. The key piece is this part here, look. And in this pattern, we see there's a single service maintaining multiple request paths. There's a constant stream coming off consistently into the service, even though the request is up and down and up and down and up and down. Yep. What you have to be careful of in this context is that this rate here that you're processing off still needs to be quick enough eventually to maintain this ingress queue. Otherwise, your queue just backs up and up and up.
Yep.
And you will see this in the event of some ticketing sites happening, where you go on and you put a request on, and then 3 hours later, you know if you've got a ticket or not.
Yep.
Yeah, and that's actually not that uncommon with certain ticketing services. But if there's a ballot for a ticket, for example, yeah, that's a not uncommon way of what's the right word? Kind of organizing that in the background, where you'll generate a random number in the back-end service and launch them all together. Gotcha. But typically, the next challenge and the next pattern that we're going to pick up on, and I think we're probably ready to move now, if you agree.
Yeah.
Which is how we answer the challenge of how can we actually make this component scale out faster, so we can sustain even more of these requests. Yeah, typically we can scale up this service. Yeah, and that's kind of answer number one, is you use a bigger service pump. Yep. So I can't think of a real way of expressing that in the analogy of our fast food restaurant. Yeah. We maybe have a wider road so you can process bigger messages, but actually they don't tend to do that. Yeah, and they don't tend to do that with a motorway either. So you don't have wider lanes to fit more cars down them. You add more lanes alongside, and that's exactly what they do at a fast food restaurant. They have at least 2 or 3 lanes for the slowest point, which arguably is actually taking your order.
Yes.
And then they'll filter into another one. Okay. So what's happening in that scenario in our application architecture is we then have multiple consumers of each message on the queue. So we scale out this right-hand side, so there's more than one thing that can pull each message.
Gotcha.
So we've still got lots of instances of things pushing onto the message queue. We've still got a single ordered stream of messages. But at this end, it's now random as to which instance of our consumer is going to take off our message and is going to issue a ticket. Yeah. Sometimes in that scenario, that includes a kind of leasing operation, or maybe you're pulling off a pool of tickets. Yep. Yeah, you just pick a random number, 1 to 10, and grab that one. Or pool 1 only issues tickets beginning with 1 or ending with 1. Pool 2 only issues tickets ending with 2, and it just keeps trying to pull off the message, and you've got 10 that eventually will issue all of the tickets until there's none left.
Gotcha.
So that kind of scenario in that. And that effectively is the analogy in the real world is I have a drive-through restaurant that has 3 lanes to take orders. In fact, actually, in this scenario, you then actually have 2 queues, right, which is actually pipes and filters. But we'll save that for a subsequent session, maybe that somebody else can. But the core part around competing consumers is I have an undefined or fixed number of consumers of the message. Yeah, to process the things which are placed by the queue-based load leveling pattern.
Yeah, and I think that. Yeah, go ahead.
After you.
So I think the magic behind this is when you start thinking about some of the more PaaS services which are available in the platform. So things like Azure Functions or app services that can actually scale based upon that queue that you're talking about then, because that's what we're talking about, is this idea of scaling out those instances rather than scaling up if we're breaking it down. So having more hands to the pump, like you say, to go and process that backlog so you can keep it going through. Now, of course, you still bringing it back to that thought from the previous page about leveling out that load and how you make sure you're processing quickly enough. How much you scale out this layer is then going to determine your next layer on, how that's going to be impacted. So you always need to think about how, when you chain these different patterns together, what the impact is going to be on the rest of the system, of course. But ultimately, that's what we're talking about there, is just being able to take more messages off the queue more quickly. That is literally their job as the worker. They are just doing that off the production line. Off they go. They send out their parcels, for example, let's put it that way, or they serve their restaurant users. We're getting all the analogies in here. And then they send it off to the next part of the process then.
Yeah. So a nice example in this is where you see smart motorways or these smart freeways out in the US, where they'll enable certain lanes based on timing or demand. So if there's more than a certain number of cars or vehicles in on the road at a certain time, they may add additional capacity by opening up a hard shoulder or diverting traffic flow from the opposite side of the road, potentially. And that's a nice way of doing that in terms of those of traffic flow. Yeah. The thing to be mindful of in this scenario is that concept of back pressure. Yeah. So where is the point in which you're going to see the bottleneck? Because if there is a chain of events, we might just be moving the bottleneck further down. So our service with our ticket issuing. So now we're in a situation, if we've implemented both of these patterns so far, we now know my website's not going to crash. Yeah. So that's the first point. It's not going to crash because we're going to queue the request, and provided the request queue is robust enough and fast enough, but those are usually PaaS services, so you don't worry about them. Provided they're good, then our request's going to get acknowledged. We get a ticket request number, for example, that gets popped onto the queue. We span out for competing consumers, and we can quickly process these. Now, if we go from 1 consumer to 100 consumers, the user won't notice. So there'll be a short spin up cycle. Cold start delays maybe in something like a function app, and bam, we'll just start picking messages off, and it will just chew its way through the queue. Unless the end store at the very end isn't capable of coping with the demand.
Right, exactly.
Which means you can still crash it, basically. But that's about dynamics of scaling and scaling different services, which is kind of it's not necessarily core to this pattern, but it's a side effect. It's a definite thing to consider.
Absolutely.
Yeah, you can still overwhelm a downstream database service by not having that scaled adequately.
Absolutely. And I think that's one of the, just for all of these patterns, really, that's one of the obvious examples, is if I'm not using a queue at all. And I've seen this with a customer recently who's been involved in some way related to some of the COVID work going on. And they were going to be speaking from their front end directly to their back end, nothing decoupling the two. So, of course, there's a couple of things that the queue then adds at that point. A, the decoupling, where if that back end gets overwhelmed for some reason, then at least the front end can still keep going until the queue gets full. Then that's a different problem. But 2, then you're not overwhelming that database as quickly because of something like a queue-based load leveling pattern then, and you're starting to bring that pressure down a bit. But I think what we're talking about with this pattern is the more you scale out that right-hand side, you're sort of turning a dial on how much pressure you're going to be putting onto that back end once again, and that's just something you need to think about, the dynamics of that as you go and change those settings there.
That's absolutely right. And that's about tuning. So there are ways in which you can make that back end throughput more dynamic. So looking at the serverless tiers of Azure SQL Database, or the serverless, or even autopilot features in Cosmos, to actually dynamically scale that data store out on demand, so it will cope with the level of demand that you need. Generally, queuing services and having a consistent load is about 80% of the way there. Yeah, if you've normally got, if you can let that message queue process and the user doesn't any longer require an instantaneous response,
Yes.
then we can let that crazy up and down pattern where it's the top that's going to kill your service and the bottoms that's going to waste resources, level that in the middle so it's consistent.
Yes.
Yeah. If it's still not enough, then we need to add more back-end resource, and that pattern looks more up here across there.
Yep. I think that's where we typically use the queue depth or something similar as a way of scaling, because similar to the traffic scenario earlier, right? Like you said, how much traffic have we got on the road? Right, we need to open up another lane. It's not, how much are we, processing through this traffic that we need to go and scale up on. It's really the traffic itself. Yeah.
Yeah, and that's how the bindings for functions work. So if you've got a service bus binding for functions, it's looking at potentially the last age of the last message which arrived and the depth of the queue in total. And if it's starting to run a bit deep, then it'll add more instances until the backlog is cleared, and then it will start to reduce them away again. And that's a really nice, elegant way of adding scalability into the middle tier of the system without affecting the front end.
Gotcha.
Well, what about if your front end thinks it needs a synchronous response? So what about if my man standing or lady or standing looking at my ticket app and they're saying, okay, I've got a ticket request, but I need to know if I've got a ticket or not before I leave, because I might be coordinating with 2 or 3 people to book as a group.
Yep.
That statement sounds a little bit strange in the face of a recent COVID event.
Yep.
Well, it's certainly something we might have done in the past.
Indeed.
In fact, even just booking a ticket for an event, it feels a little bit strange now. So let's suppose we're going to do that, and you need to know before you leave the site. So you can't just fire and forget an async response that gets popped onto a queue and then you get told about it later on whether you've got a ticket or not in the ballot. You're actually going to pay for it right now and you want to know. Yeah, or maybe the ticket provider wants you to pay for it immediately if you've got a request.
Yes.
But they don't know whether your ticket's actually allocated or not because they've just queued it asynchronously. And that brings us on to what is really a very common pattern, but it's not described that much as such, which is asynchronous request reply. And in that concept, we decouple processing of the back end via queues. Yeah, and you use queue processing and competing consumers to scale out that middle tier so it's faster. But it's not a true asynchronous connection in this case. So if I've got a browser or a middle tier API or anything that's actually doing this kind of, that is able to say, go do this, put this message on the queue, we can fake a synchronous response in the browser or a polling response in the browser by using an intermediate API.
Right.
Yeah, I'm just going to, the fastest way to describe this is with a picture.
Yep.
And we actually have 2 pictures here. So this one is showing you the flow, which to all intents and purposes is a very technical diagram showing we actually make a call to the API, which is this. What comes back is an accepted response, not an OK. So it just says, yes, we've queued it. And then we poll this status endpoint over and over again. So we know either it has or has not responded. And if it hasn't responded, we get another 202. Yep. If it's still not complete, we get another 202. So I don't know at this point whether I've got a ticket or not. Once I have or haven't got a ticket and I've got a response, my status endpoint should then return me a redirect, so a 302, to the end resource, which is my status of my actual object. And the browser or the intermediate API follows that redirect and gets the result of their operation.
Yep.
Yeah. So the work was queued on a random consumer, was carried out by something that was completely disconnected from my calling client. I got the response and the status poll from something that was also completely disconnected. But to the client, to the consumer, it looks like it was all one operation because all I did is a repeated poll to a status endpoint and got a response.
Yep.
So it's a minimal amount of recoding in this scenario. It's like a very small shim. You can even implement this with a single endpoint that has a facade over the top of this whole process and make it look completely synchronous at the expense of holding lots of long-lived connections. Yeah. What we see in more modern architectures is something like Signal R being used to implement this.
Yeah.
Yeah, so you'll actually have a single channel rather than the open connections where you'll fire those. But there's a lot of architectures, a lot of, in fact, not even legacy. There are a lot of architectures which are actually very, very modern, but are developed based upon REST type semantics that will not handle a signal callback channel.
Yep.
Yeah, and the particular one is if you're calling another service rather than calling a browser. But this is a really elegant and actually remarkably simple set of semantics for processing this. And let's just show you this piece down here. So here's an example, and this is using functions. So what's happening in here is point one, my website, my client does a call to my API that says, I need a ticket. The reply that comes back from my function is two parts. Number one, it queues a message onto a message queue.
Mm-hmm.
Yeah, in fact, that's actually number two. But number two and number three are the key pieces here. So number three, the reply that comes back isn't a complete reply. It's simply a 202 with a header of a location. And that location points at the status endpoint that says, when I'm finished, the response will be over there.
Mm.
Okay. At that point, we pause. We take a 5-second timeout, a 2-second timeout, whatever we choose to do, depending on how long you expect this to actually be processing for. And you can vary that number based on the length of the queue as well, if you want to. Yeah, so it's not outside the realms of possibility to have an introspection process checking the queue
exactly.
every so often.
It could be something which the actual function itself, just as part of the response back, goes ahead and just inserts into that header. Exactly.
Yeah, I mean, you probably want to cache it every 2 or 3 seconds, maybe, if you're going to do that, because you wouldn't want another 100,000 queue length requests coming in. But certainly you could vary that based on the amount of load coming in. Check it every so often, and at that point there is then the reply. I think it's a retry after header that's set the HTTP level that says try again in 1 minute, try again in 20 seconds. So it will then asynchronously call that status endpoint at number 6. Yeah. Notice I haven't said 4 or 5 yet.
Yep.
But number 6, my web client will call number 6. The next thing it will see, it will go away and check for the result. The result won't be present yet because my queue processor hasn't actually processed the message, depending on how long that reply was. So what's more than likely is it will back off. Yeah, back off, retry shortly.
Yep.
In the background then, one of my competing consumers, so I've only got one function here, but this could be a function app that has 5 or 6 scaled out hosts behind it, or 20 or 30 or 50 scaled out hosts that are all consuming my message as one app, which will go in, we'll go and check the next available ticket if there is one. And if there is one, we'll allocate that ticket and write the result to that storage blob, which at the next time my client calls into it, we'll actually call the status endpoint, we'll check the blob, and then we'll use the valet key pattern, which I don't know if you've talked about on a prior session or not.
I don't think we have yet, no.
Okay, so we'll use a valet key pattern, which is one to investigate potentially for future reference, to issue a shared access signature to redirect the client to the actual response.
Yep. I think we're aiming to get that one in January, actually, with Peter. So, yes, that one will link in nicely.
Well, there's a nice lead in for you to talk about a valid use of that.
Absolutely.
Yeah, that's let's go back to our real world analogies that we've had for the last couple. Yeah, so that's almost like the traffic light below. Yeah, so it's actually, is this green or is it red? Do I have to go and park in a bay to go and get my food?
Yep.
And wait for it to arrive, or do I just get it at the next window? Yeah, so the last window is going to be your status endpoint, whether you get diverted out or whether you actually receive your response immediately.
Yeah. Sense.
The advantage of that is it really kind of offloads that status and work checking to another endpoint. So these might be completely separate function apps. And they could also be separate storage accounts.
Yep.
Yeah, so your queue and your storage, if you're using Azure Queues, Azure Queue storage, might not be the same one as the storage blob itself. That might be backed away, and then you get scale out across all of your different instances.
Makes sense. And I guess we've talked about 3 different patterns here. So queue-based load leveling, competing consumer, asynchronous request reply.
Yep.
And I think in terms of the story that we've told, it all makes sense. You know, that high load scenario, high throughput, and then being able to start pushing or maybe massaging where the pressure of the system is and being able to distribute that out. Where would that, I guess those 3 patterns, where would they not make as much sense? Because I guess it's quite obvious for, you know, the scenarios where we've got that high load, but are there scenarios where maybe it wouldn't be such a good thing to use some of those aspects?
Okay, so let's take those individually then, maybe.
Sure.
Yeah. So where the chunks of work are very, very big. So if it's not necessarily a kind of a micro API that's doing ticketing, that's the example we've used. If you've got more of a batch-based process, which is queuing a massive chunk of work, then you might use a modified version of that pattern. So Azure Batch APIs are similar to that, where you're still queuing a job to run on a pool. You're still providing an input and an output and some kind of process to it, but you wouldn't necessarily use an Azure function for extended runtime. You might choose to use a kind of more HPC cluster batch API type approach with a batch scheduler. Equally, if the workload that you're providing has a very, very big block of data to process, you might choose to combine this with another pattern. There's a pattern up there called claim check, which other people might choose to talk about later or might have already talked about on here, which is basically posting a big block of data somewhere else, and you just consume that from the queue. So there's a couple of modifications to the pattern that you might see. If your backend is fixed, so that's the case we see with some document and infrastructure stores. So if you've got a MongoDB VM running somewhere, and it can only handle a certain amount of throughput, and to scale it up, you'd have to reboot it potentially, and you can't scale it out. Then competing consumers may not make that much sense because the back pressure will quite rapidly overwhelm the downstream service. So if you've got a fixed component that you can't re-engineer out, which does happen, right? Sometimes, maybe you're calling a down. In the example of our ticketing service, that might be a third-party payment processing API. That doesn't scale out particularly well, and you might need to bring in multiple payment processor APIs in the back end. So or maybe with a circuit breaker between them. So you overwhelm the one, you switch to another one. And
that's a really, really good point, actually. It's something you and I have talked about many times and given many talks on around the idea of knowing your dependencies. And it's not just about knowing your own dependencies, but if you've got any third-party dependencies as well. So the payment provider example, quite often we'll see when we work with customers is that, you know, they've probably got most of the dependencies that they have in their architecture on the diagram, but it's those third-party ones or the ones just not really in their control that they miss, and it's quite likely that those are the ones that would then trip them up along the way as well. So, you know, making sure that you include anything that you might need to depend on, not just what you control, but also then have you thought about the agreements you have in place with those third-party processors and whatnot, and how you then scale as well is equally as important.
Yeah, and possibly second sourcing in that case. So payment providers are one, right? But I've worked with a few other customers in that space, and one of which I know you've worked with me on as well, where all sorts of service provision. So something that's especially in financial services where you can't perform a transaction without certain things being present. So if you're providing credit, for example, you might need to credit check with a credit reference agency. You might need to have some kind of credit underwriting occurring with the backend API before you can perform a retail transaction. And all of that might be going through a queue. So if you push that through a queue, you need to know the different stages of that confirmed. Without going into pub sub here either, that might be a way you've got multiple processes running off the back end of one of these, and they might also all be participating in an asynchronous request reply. That's actually quite an elegant variance on this. Is you don't just have to have one consumer running between step 4 and 5. If you need to do a credit check and you need to do some kind of underwriting and you need to do something else like an address verification, you can actually trigger all three of those in parallel.
Yes.
And then have your status endpoint check for which blobs are present and return all three together.
Exactly.
So it's quite a nice parallelization pattern as well.
Nice. Excellent. Good. So I guess that's the 3 patterns that we've covered there. We've talked about some of the kind of considerations as well, or some of the issues that might come up. Just conscious of our time and starting to wrap us up. Yep. What would you leave really with the folks as top of mind thoughts from these 3 particular topics? Is there anything of everything that we've said here that this is critical to get right? These are the things that you really need to think about here, or this is one thing you should really take away?
Okay, so I guess using the patterns together and the other patterns that we've also touched on, the circuit breaker and claim check, investigating those to see if they're going to help you out in terms of what you're trying to do are definitely sensible. The ingress queue and back pressure are critical in these patterns. You don't want to be overwhelming a downstream service. You want to use this to protect the downstream service from being overwhelmed. So potential limiting the bound of scale of competing consumers. If you have an infinite number of competing consumers, you're pretty quickly going to kill your downstream service. Yep. Yeah, the key point is you want to be able to throttle that somehow. And there are settings in most of our services that you're running to not have unbounded consumption. Sometimes unbounded consumption is great, right? You can chew through tons and tons of work really, really, really quickly. You can also chew through tons of cost really, really, really quickly. So depending on what you're doing, that might be relevant for you. You might want to throttle some of that back to get to an acceptable setting. I guess if there was any key takeaway, I'd love to see the consumers of your sessions looking at these patterns and trying to see how they can apply them together. Yes, so look at this situation you're trying to engineer around and start with queue-based load leveling and work your way forward on from there to see which ones of these components can be aggregated together and combined. Because the truth is you can come up with an Uber architecture that has everything on the left-hand list of what we're sharing here, right? And more besides. And you can rapidly build a really, really scary, really, really complicated, completely unmanageable service, when actually all you needed to do was to scale to meet a peak in demand. So apply them, look for them, understand what they are, but apply them with respect.
So the reason I'm smirking right now is Steph and I recently recorded a session on CQRS, materialized view, and event sourcing. Yep. And that's the exact same discussion we said there, which is, yes, these patterns are well-known patterns and they can absolutely apply in scenarios, but you need to check that the scenario is right for you. And that always comes back to our favorite word, requirements. What are you trying to solve? What are you trying to meet? Because the worst scenario is you've got a system so complicated that no one can manage it, or some people can manage it, but then when those people leave the team, you're then in a mess because it's so complex no one can understand it. And there's that balance of kind of real world implementation versus the theoretical side of the patterns and what you're trying to achieve. So love what you said there, Will. I think that's a really good point.
That's actually a really good point. Yeah, that's actually a really good point, and it's one that might be worth. I don't know you're trying to wrap, but just give me one last key here. Yeah. What we're touching on here is where the architecture center patterns start to transition from cloud architecture into modifications to general software architecture. Yeah, and back again, right? So if you start to speak to somebody about queue-based load leveling, that's great. So we can decouple stuff to a queue. The next thing to think about is inside your software, what would you decouple to a queue and what should it do at the other end? And if you apply that to a classical enterprise app, what you're going to end up with is, I want to queue all of my writes. And then you're rapidly into CQRS and event sourcing and all the things and the niceties you talked about with Steph. You're also ripping apart the internals of your software application. Right, so you can apply these together, and there's absolutely valid reason for doing so from a software architecture point of perspective. So requirements engineering becomes critical. Equally, the point of the async request reply pattern itself is so you don't have to rip it all apart. Yeah, it's to be able to shim queue-based load leveling and competing consumers inside an existing application architecture with minimal change. So you can extend parts of your software architecture and leverage modern cloud patterns without having to tear it all apart and bin everything. Yeah, so that's the key. That's the difference. You can go full on steroids and black CQRS, event sourcing, choreography, claim check, valet key, everything in here. Yeah. And what you'll end up with a really elastic software architecture. But that elasticity comes with a consequence if you do that. So it comes with a consequence of increased complexity. And that's when you're into, in fact, with queues, actually, you're into a little bit of this, into distributed debugging.
Yes.
And you have to have some kind of distributed tracing running, something like Application Insights for Azure. Other services are available, but Application Insights is the key piece in Azure Monitor. So understanding when my call left my API and got queued, and for some unknown reason, I didn't get a response to my status endpoint, or my status endpoint threw an error. What's the chain that happened, and how can I go and investigate that? And that complexity is one that I sit in the fence, right? If it's valuable enough to hit the requirements you've got, do it. Yeah, and that's the key. Do the complexity, because you can manage complexity. If you're just doing this because it's cool, yeah, because it's modern and because it looks clever and looks like a modern architecture, I would argue that's not necessarily the right reason to be doing it. But we see a lot of that.
We do.
See a lot of people come in, they just chuck cloud patterns at a piece of software that actually, you know what, that scaled really, really well as just as a monolith.
Yeah, exactly. Good. I feel like that's potentially leading on for another session for us to go and focus on as well. But I'll wrap us up here. So Will, another great session there. So thank you for talking about all three of these, and I'm sure we'll figure between ourselves of everything we've spoken about there what we talk about next time as well, and bring you back to talk about.
No problem. Thank you. I look forward to hearing Peter's session with interest as well.
Good stuff. Thank you, Will, and thank you again for joining. So, we've talked there about 3 different patterns. We've talked about queue-based load leveling, we've talked about competing consumers, and we've talked about asynchronous request response. So lots and lots of detail in there, detail around the scenarios where they typically work, scenarios around where they may not be such a good fit, and some of the key considerations as well. And just like we said in the session with Steph, around CQRS, around event sourcing, around materialized view, make sure that you use all of these patterns in the scenarios that you really need them, not just because of the sake of using the patterns and building these theoretical systems. When you introduce these patterns, you introduce complexity, and you need to make sure that you're targeting that for a particular reason. And as long as you've got your requirements in mind and you're driving towards those requirements, then the complexity may be worth it. But if you are just building for the sake of building it, that's where you need to take that step back and just evaluate what you're looking to achieve there. So another great session. As always, please do subscribe and share with anyone that you think may find the content valuable. And of course, we'll be creating more content similarly around these topics as well. So that's it for today. So until the next time, thank you for watching, and bye for now.